like to thank Professor Sano for giving me an opportunity to talk at KAIST. Today I will talk about Meteoroids on convex geometries. This is based on my PhD thesis, and I will talk about this. And my major is Matroid theory and graph theory, and some discrete optimization. For more information, please check my homepage. Okay, now I will start. The contents of my talk is as follows. First, I will talk about some introduction, and after then, I will talk about convex geometries to define some Matroid structure on it. And third, I will give the definition and examples of Matroids on convex geometries, and we call this kind of structure CG Matroids. And after then, we discuss some subclasses, operations, and optimizations on CG Matroids. So let's start. The notion of a Matroid was introduced by Hassler-Whitney in 1935 as an abstraction of the notion of linear independence in a vector space. And after he introduced, it found that Matroids have many applications in electrical networks, rigidity problems, and special graph theory, and so on. So many researchers have been studied Matroid theory. And today, CG Matroid is a Matroid structure on a convex geometry. And this is introduced by Fujishige, Kosheboy, and by myself in 2007. So, and there are many kinds of generalization of Matroids, something like polymatroids, super Matroids, POSTECH Matroids. And this CG Matroids is generalization of ordinary Matroid, of course, and includes in POSTECH Matroids. That is, Matroids are defined on just finite set, and POSTECH Matroids defined on partially ordered set, and CG Matroids is defined on convex geometry. This is a generalization, and I will talk about this kind of things. And this is just a picture of my talk. First, I will talk about convex geometry. After then, we define CG Matroids and talk about some basis of CG Matroids, independent sets and spanning sets. And after then, we will discuss some subclasses of CG Matroids called strict CG Matroids and co-strict CG Matroids. These subclasses are led naturally from the axioms of independent sets and spanning sets, respectively. And we show some examples and some relation to operations, restriction and contraction and something. And finally, I will talk about some grid algorithms on CG Matroids. Okay, now start. Oh, sorry. First, I will give the definition of convex geometries. Let E be a non-empty finite set, and let script F be a family of subsets of the set E. Then we call the pair EF a convex geometry or an abstract convex geometry if the family F satisfies the following three properties. The first one is the empty set and the set E is in the family F, and the second one is the family F is closed under intersection, and the third one is for any element in the family F but not the set E, there exists an element E in E but not in X, such that X with the element E is also in the family F. If F satisfies these three properties, then we call EF a convex geometry. And we call each element in the family F closed set. This is also called a convex set. And this notion was introduced by Edelman and Jamison in 1985. And this notion is Indeed, this is a dual of anti-Meteoroid. I don't explain about anti-Meteoroid, but this is a dual of anti-Meteoroid. Okay, now I will show you some examples of convex geometries. So let E be a finite set in D-dimensional space, and let F be a family of subsets of E and X such that the convex hull of X intersection the set E is equal to X. So then this pair is satisfies the definition, and this is convex geometry, and this kind of convex geometry is called a convex sharing. And this is a picture of this, for example. This is 9 points in R2. Then this 6 points is a closed set, because the convex hull of these 6 points is something like here, and the intersection, the set E, intersection 9 points is equal to the original 6 points X. So this is a closed set of the convex sharing, the convex geometry, but this 4 point is not in the family F. This is not closed set, because the convex hull contains another point in E, so this is not a closed set. This is an example. And the next example is, okay.
Let's see the second axiom.
Okay. Second axiom is if X and Y is in the family F, intersection. Oh, sorry. CG2. If we have some closed set, then add one element out from outside. Okay. So, for example, in this case, we can add this one, yes, or this one, anything in this case. Okay. So the next example is let T be a tree. This is a connected graph without cycle. And let F be a family of subsets of the vertex set of the tree, and such that that is the vertex set of some subtree of T. Then the pair V and F is a convex geometry. This is called tree sharing. And this is also a picture. This is closed. This 3 points is a closed set, because this forms subtrees. Induced subgraph forms subtree. But this 3 point is not closed set, because this is the induced subgraph is not connected. So this is not subtree. So this is also an example. And the third one is POSTECH. Let P be a POSTECH on the ground set E. And a subset of E is called an ideal of the POSTECH P if the following property satisfies. That is, an element Y in the X. If we take Y, then the lower, any element lower than Y is also in the set X. Then we call this kind of set X an ideal. And let F be the set of all ideals of the set of the POSTECH. Then the pair EF is a convex geometry, and this is called a POSTECH sharing. So ideal means something. If we this means this is bigger than this one, and this bigger than this one. If we consider a POSTECH, and then something like lower set of the ground set, lower set is a ideal. So this is closed set, but this kind of subset is not a closed set, not ideal, because this element is lower than this element, but not in the set. So these are the examples of convex geometries, and convex geometry contains this kind of POSTECH sharing convex geometry. So this is, we can consider convex geometry is a generalization of a partially ordered set in this way. So now I will define two more things about convex geometries. Let EF be a convex geometry. Then for any subset of E we define the closure of X is the set, we denote tau X to be the set of the intersection of Y such that Y is closed set and Y contains X. So in other words, tau X is the minimal closed set which contains X. So for example, this is in R2, 9 points, convex shading. And if we take X as these 4 points as X, then the closure of this X is this 5 points, because this closure, in this case, closure is equal to the convex hull of X. So this 5 points is the closure of that 4 points. And one more thing, for a closed set X, we call an element in X an extreme point of X if X and the set X minus the element E is also a closed set. So for example, this black 8 points forms a closed set. Then the extreme points of this X is these 5 points, because if we remove this one, and the remaining points forms also a closed set. But this is not an extreme point, because if we delete this one, then that is not closed set.
Does every convex set have extreme points?
Yes, always have.
And is it some fixed number related to the convexity, or how does...
No. Does the axiom says the convex set has extreme point?
That means any element in F.
Yeah, you can add one element.
Yeah, that is the definition.
Right.
And from the definition, we can induce using we can prove that using this condition, because closed under intersection, we can show that always.
Because there is a chain.
Yes, indeed, yes. This axiom is indeed equivalent to that all of maximal chain has the same length, the number of E. So yeah. So this is not any closed set have always extreme points, and we denote all the set of extreme points of X by EXX. So we defined tau X and EXX. Okay, now I will show you the definition of CG matroids. Okay, let EF be a convex geometry, and let script B be a non-empty subfamily of F. Then we call the pair EF and script B a CG matroid if script B satisfies the following two properties. The first one is this is a clutter. Clutter means for any B1, B2 from here, if B1 is contained in B2, then indeed B1 is equal to B2. This is a this is a clutter. And the second condition, second property is called middle base property. That is the following. For any xy is in F and B1, B2 in script B, such that B1 contains X, Y contains X and B2, then there exists some element B in the script B such that X is contained in B and Y contains B. So this means if we have X and Y and B1 and B2, and X is contained in both B1 and Y, and Y contains X and B2, then there exists some element B here that is contains X and contains X and contained in Y. This property is called middle base property of matroid. So if script B satisfies these two properties, we call CG matroid. And I remark that if the convex geometry is the trivial one, that means script F is equal to the set of all subsets of E, then this definition is completely equal to the one axiom of Matroids, ordinary Matroids. So in this sense, CG Matroid is generalization of a Matroid. And one more, we call an element in script B a base. This is the definition of CG Matroids. Now we will see some examples of CG Matroids. Okay. Let E be a finite set in D-dimensional space, and we consider EF a convex sharing. The first example of the convex geometry, defined like this. Then we define script B be the set of closed set such that the cardinality of X is equal to the dimension of convex halo of X plus 1. This is also equal to the dimension of convex halo of the whole set E plus 1. Then the pair EF and B is a CG Matroid. This means, how to say, this example again, in R2 there are 9 points. In this case, these 3 points is a base, because this means, what do you say, script B is the set of all maximal simplex which does not contain other point inside. Something like such kind of family, we can define CG Matroid. And we call this kind of CG Matroid affine Matroid, affine CG Matroid. And the second example is, if we take a tree sharing and we take script B as a set of some subtree of fixed size K, then this is also a CG Matroid. Indeed, this example is more generally for any convex geometry EF. If we define script B be the set of all closed sets having cardinality K, then this is a CG Matroid, and this is we call K uniform CG Matroids. And if the convex geometry is equal to POSTECH sharing, in this case, CG Matroid, the definition of CG Matroid is equal to POSTECH Matroid. We didn't talk about POSTECH Matroids, but in this sense, CG Matroid is also a generalization of POSTECH Matroids. Okay, now this is the first theorem for CG Matroid. This is the following. All the bases of CG Matroid have the same cardinality. This is a very fundamental result on CG Matroids. And the next theorem is more interesting and important. This is called exchange property for bases. And okay, let EF be a convex geometry and the script B be a family of subset, closed sets. Then this is a CG Matroid if and only if script B satisfies the following exchange property. The exchange property is if we take two bases B1 and B2 and we take E1 from here, then there exists an element E2 from here such that B1 minus E1 union E2 is also a base. So in ordinary this is some kind of exchange property, and I will explain this set now. Okay. Let's consider 12 points in R2 again. We consider a convex geometry, in this case convex sharing. And we consider script B be a 4 uniform CG Matroids. That means script B consists of the closed sets of cardinality 4. So for example, this 4 points is a base B1, and this 4 points is also a base B2. This B2 is also a base. So then this set means B1 union B2 and closure, take a closure, then this 8 points, and we take extreme points, then extreme points of this set is these 5 points, and not in B2. So these 3 points is not in B2. So we can take any one from here in this case. And then there exists E2 is in here. This is in the closure of B1 union B2. So from this 8 points, but not in B1. So E1 exists in these 4 points. So this is the exchange property for CG Meteoroid, and I remarked that remarkable difference between ordinary Meteoroid and CG Meteoroid is here. In ordinary Meteoroid, the element E2 is always in the another base B1, B2, but in this case, we cannot say that E2 is in B2. Sometimes it is in outside of the base B2. So that is very different from ordinary Meteoroid or POSTECH Meteoroid and general CG Meteoroid. Okay, now I will define something more. Let EF be a CG Meteoroid. Then we call the closed set an independent set of the CG Meteoroid M if X contained in some base. And we call a closed set a spanning set of the CG Meteoroid if the closed set X is contains some base B. This is the definition of independent set and spanning set. And now after that, I will give an action for these kind of things. Okay, now I will discuss some subclasses of CG Meteoroids. So first, let's recall the actions for independent sets of an ordinary Meteoroid. That is, if E is a finite set and script I be a family of subsets of E, then the pair EI is an ordinary Meteoroid if and only if script I satisfies the following 2 properties. Script I is called a family of independent sets. That is, any subset of an independent set is also an independent set, something like this property. And augmentation property. Augmentation property is, there are several kinds of augmentation properties. Here I wrote 5 kinds of augmentation properties. Maybe the first thing is the most popular augmentation property, I think. If 2 independent sets and the size is the difference, then there exists some element and we can augment. And they are a little bit different, something like this. And I comment on this one. On set theoretically, these 5 properties have the following relation. The 5th one is the most strongest. This implies A1, and A1 implies A2, and also A4, and A4 implies A3. This is the weakest, and this is strongest. And this is just set theoretically. But if script I satisfies I1, the property I1, then these all 5 augmentation property are equivalent. So in ordinary Meteoroid theory, these 5 augmentation property, we can choose any of this one as an action for ordinary Meteoroid. So now I will show you the characterization of independent sets of a CG Meteoroid. Okay, let EF be a convex geometry and script I be a subfamily of the family of closed sets. Then script I is the family of independent sets of some CG Meteoroid if and only if script I satisfies the following 2 properties. The first one is any closed subset of an independent set is also an independent set. The second one is, this is augmentation property, in this A3 type augmentation property. A3 type is the weakest one. We can characterize this type of using this type of augmentation property. That is, if we take two independent sets, and the cardinality of I1 is smaller than I2, and I2 is maximal independent set, then there exists some, we have to take some closure here. There exists some element E, and this is also an independent set. So the difference is here and here compared to original Meteoroid. And we can, from this characterization, we can introduce some subclass of CG Meteoroids, because this characterization using just the weakest one. So if we assume more strong augmentation property for some family, so then we can define some subclass logically. But I don't know, we don't know really subclass or just a defined subclass. So first let's define strict CG Meteoroid by using A1 type augmentation property. A1 type is in the second strongest one. This is maybe the most ordinary one, so we use this one. The difference is I2 must not be, may not be maximal in independent sets. So now this is indeed real subclass or proper subclass of CG Meteoroids, because they are non-strict CG Meteoroid. This is a this is an example of non-strict CG Meteoroid.
So can you write the definition on the so that we can see?
Oh, sorry. Okay, I see. Okay. Okay. This is convex geometry, and let the script I be a subfamily of F, and I is the family of independent. Okay, this is the family of okay. Wait a moment. This is a CG Meteoroid if this is a characterization. If I satisfies I1, that is X is closed set and I is then, and the second one is difference. Okay. In ordinary case, we must assume the maximality of for I2. That is the difference. So if we delete this one, then this is the definition of strict CG Meteoroid. So in this case, don't assume, then we can augment some. Okay. This is a characterization of CG Meteoroid and definition of strict CG Meteoroid. The difference is here. And an example is, let EF be a convex shading in R2, consists of 5 points. And that means, okay. And let the script be the family of these 4 sets, 1, 2, 3, or something, something, something. Then this is not a CG Meteoroid, because if we take I1, 1, this is an independent set because this is contained in a base, and I2 4 5 is also an independent set because contained in this base. So we have 2 independent sets, and the cardinality is, of course, I2 is more bigger. And in this case, I2 is not maximal. This is not base in this case. So if we can augment, then we can take from here some element. Oh, sorry, exist. Something exists. This is just 4, 5. But if we add 4 or 5, both of these sets are not independent sets. So this example does not satisfy the the definition of strict CG matroid. But of course, if we assume this one, it satisfies. So this is not strict CG matroid. And we can characterize strict CG matroids as follows. If we use we use this A1 type augmentation property as the definition of strict CG matroids, but indeed A2 and A5 types augmentation properties are also equivalent under this condition. And before we characterize by A3, but also A4 type characterize ordinary CG matroids. So in ordinary case, all augmentation properties are equivalent, but in CG matroid case, it separates two parts, something like this. And okay, now I will talk about spanning set. The story is almost goes similarly. First, recall the actions for spanning sets of ordinary matroids, and that is if E is a finite set and S is the family of subsets of E, then the pair ES is a matroid if S satisfies the following two properties. The first one is any set containing the spanning set is also a spanning set, and some reduction property. And also there are several kinds of reduction property. I wrote here 5 reduction properties. And also they have some relations between action properties. This is strongest and this is weakest. And if S satisfies the first property, then all 5 properties are equivalent. But in CG matroid case, we can characterize the family of spanning sets by the weakest reduction property, R3 type. We didn't explain the detail, but we can characterize this one. And in this case, we also define some subclass similarly by using more strong reduction property. Here we use R1 type reduction property. Then this is indeed a subclass of CG matroids. We can consider some example for non-constrict CG matroids. And similarly, three of the 5 properties characterize constrict CG matroids, and the other 2 characterize ordinary CG matroids. So this is also a subfamily of CG matroids. And indeed, these 2 subclasses contain POSTECH matroids and ordinary matroids. Okay, now I will talk about some operations on CG matroids, such as restriction and contraction. These operations are closely related to the subclasses strict CG matroids and co-strict CG matroids. Okay, now the definition of restriction. Let M be a CG matroid with the family of independent sets, and let X be a closed set. Then the restriction of the CG matroid M to the closed set X is defined to be the following. The ground set is X, and Fx is defined to be the set of closed sets contained in X. And script I is defined to be the family of independent sets contained in X. Then we can define the pair something like this. And if M is a CG matroid and X is a closed set, then the restriction satisfies the first property. So then how about the second augmentation, the second one, augmentation property? There is a theorem. If the closed set X is a spanning set of the CG matroid M, then the restriction is also a CG matroid. If the closed set is spanning set, then restriction is the CG matroid. But this is non-strict CG matroid again. If we take a closed set which is not a spanning set, then the restriction may not be a CG matroid. This example shows this one. If we take some, this is not a spanning set. If we take this one and consider some restriction, then we can show that this is not a CG matroid. So for ordinary, for general CG matroid, restriction is not so good operation. But if we restrict the class to the class of strict CG matroids, then if we take any closed set, then the restriction is always a strict CG matroid. So strictness is very closely related to the restriction. Okay, now we will talk about I will talk about contraction. Contraction is defined to be the following: if let M be the CG matroid with the family of spanning sets, and let X be a closed set, then the contraction of M by X is defined to be the pair something like this. The ground set is E minus X, and Fx is defined to be the Y minus X. Y is a closed set, contains X, and Sx is the family of S minus X. S is the spanning set, contains X, which contains X. Then we can define this this way, and we can check that the first property of the induction contraction satisfies this property. So then how about the reduction property? Similarly, there are some theorem. If we take a closed set as an independent set of the CG matroid, then the contraction is always a CG matroid. This is a theorem for general CG matroid, but this is non-constrict CG matroid example. And if we take non-independent set as a closed set, then the contraction may not be a CG matroid. So contraction is not also good for general CG matroid, but we can show the following. If the CG matroid is a co-strict CG matroid, and X is any closed set, then the contraction is always a co-strict CG matroid. So co-strictness is very closely related to contraction. So we show that CG matroids restriction go well just for spanning sets, but for strict CG matroids we can use any closed set, and for contraction if we use independent sets, then the contraction is also CG matroid. But if for co-strict CG matroids, we can use any closed set. Okay. So finally, I want to talk about some optimization problem on CG matroid. Now we will consider maximum base problem. Okay. Let M be a CG matroid with a family of bases, and let W be a weight function on the set E, and we want to maximize the sum of weights of one element of elements of one base. So we denote WB. We denote by WB the sum of this one, and the condition is B is a base. We want to find which base is the maximum. We want to find maximum base. And also, this is maximum independent set problem. Similarly, this is CG Meteoroid with, I wrote here CG independent system. CG independent, this is more generalization of this problem. CG independence system means we just assume the first one. We does not assume the augmentation property for script I. So just this property we assume for this script I, and we want to maximize. We also call independent set of the CG independent system. We want to find maximum independent set. So okay, because base is indeed maximal independent set. This is more general problem, and we will consider about this problem. Okay, maybe I will write down MISP for short, maximum independent set problem. Okay, and we will consider efficient algorithm called greedy algorithm. Greedy algorithm is the following algorithm. That is, first we have I0 as an empty set, and we will iterate the following. For from I is equal to 0 to n minus 1, n is the cardinality of the set E. Do the following. If there is an element that is in outside of we have II, such that II with the element E is also an independent set. If there is such an element, then we choose such element of maximum weight, and we add this element, and we define new independent set, and to go to next step. And if there is no element outside, and we can choose, we can add, then we will stop and output our set. This is a very simple grid algorithm. And okay, so let's see an example. Let this one VF is a tree shading defined on 6 points, and let script I be the family of closed sets of cardinality at most 3. So this is 3 uniform CG Meteoroid on the tree shading, and let this is weight on the set E. Then if we use the greedy algorithm, then first we will take V3, this is the biggest one, and the next we can take just from here, we can choose V2 or V6 or V4, because this is independent set, but this is not independent set. So then we will choose biggest one, V6, and after then we can choose from these 3 points, we choose this one, and then we finish the grid algorithm, because already the cardinality is 3. So in this case, grid algorithm will output V3, V6, V4, and this weight is equal to 25, and this is the biggest one. So this is an optimized solution of the problem. In this case, grid algorithm go well. Okay, one more example. This is the same CG Meteoroid on tree shading, and we take some other weight on here. Then we take first the biggest one, V1. The next we can choose just only V2, because this the other thing does not make independent sets, so we have to take V2 and next V3. So grid algorithm gives V1, V2, V3 with weight 13, but this is not an optimal solution of the problem, because indeed V3, V4, V6 here, this gives weight 19, so grid algorithm sometimes fails for some weights. So what is characterization? Characterization is the following. Let EF and I is a CG independent system. Then for any weight with the condition natural, for any weight, the grid algorithm always gives an optimal solution of the problem if and only if the CG independent system is a strict CG matroid. So in ordinary matroid theory, we don't need some condition on weight, and this is always matroid. But in this case, we have to restrict some weight, some naturalness, and this characterizes strict CG matroids. So here, weight is natural means something. This one, it satisfies the following condition. If we order an element from biggest one to the smallest one, then the first I element is always closed set. So E1 is closed set, E1, E2 closed set, E1, E2, E3 closed set from 1 to n. So this is a condition for weight is natural. Okay, this is the characterization. And if we, this is an example. If we take non-strict CG matroid, even if weight is natural, but grid algorithm sometimes fails and does not give an optimal solution. This is an example, but I don't explain. Okay. I will finish talk here, but I will talk about some further study on CG matroids. One open problem is the following: an intersection theorem for CG matroids. I want to know the following will hold or not. The maximum, if we have two CG matroids with independent sets I1 and I2. This is called the rank function, but I didn't explain today. The maximum maximum cardinality common independent set. The cardinality is equal or not, I don't know, the minimum of the sum of some rank functions. Of course, we can show easily that the inequality maximum is less than or equal to minimum we can show, but we don't know this is hold or not. And I remark that for POSTECH matroids, this kind of intersection theorem is hold. This is shown by Evatardes in 90s. So I want to know this one. And one more problem is I want to characterize some affine CG matroids, something like linear matroid or something. And a theorem for convex geometries is known, that is, every convex geometry is indeed a generalized convex shading. So we can, indeed, convex geometry can be represented in RD with finite points. This is a little bit generalized. There are some K and some condition. This is definition. But this characterization shown in this entry, and I want to consider about some generalized affine CG matroids. Okay, now I will finish my talk. Thank you for your attention.